Okay, I think we're streaming now. So just waiting to hit the pause button on this one screen that always pops up. And then we'll be talking. I think we're on pages. You know what? I don't remember right now. Let me look it up. So we are. Page 23 in the workbook, page 23. And all right, let's go ahead and do it. Actually, I'm going to shut this door over here too. Okay, page 23. I'll start with the screen share. Oh, and there's something in the chat there. Let's check on that. Whoops.
Sorry, kind of unrelated, but
Okay. Yeah, that's fine. That's fine. to Jacob, to answer your question, that's fine. Okay. All right. So we got the live stream rolling. I remembered that. We got screen share. Let's do that. So page, whatever I said, 23, 22, have them both open if you can. So let me just go like this a little bit. Whoops, I think we're just after that. We had talked about that a little bit last time. Sorry, I got the wrong page here. There we go. All right. And so just a quick reminder of some of the stuff we ended with last time. We talked about potential energy. Whoops. And we are going to use that equation right here. So what does that mean on a graph? F sub x is negative the slope. Some quick reminders on this. Equilibrium is the word that means no net force or whatever. So here, if we have zero force, slope is zero, equilibrium, all of those are equivalent statements. We have stable, unstable, and neutral. More on that in a second. There's that marble analogy. You're going to keep hearing me harp on that a little bit, where I talk about, okay, which way would the marble roll? Does this marble tend to roll towards the right side of the graph or the left? That'll explain which way it moves. The steeper the slope, the faster it would roll, the larger the force in that direction. Units. We've got nanometers and we've got EVs. 1 EV is this. And then oftentimes the units used for these energies in real life problems might be MeV. When I say real life, I'm thinking about chemistry, quantum mechanics, electrical engineering. Those are common volts. Common units, milli-EV, milli-electron volts. Okay. So regarding the stable, unstable, remember that the stable is down here at the bottom of the well. The unstable is here at the top. Neutral is a flat region, extended flat region on a plot. Okay, that's kind of all of our basics from last time. And we talked about this one last time, but let's look at this one. Okay, Leonard Jones, that's the right spelling. And then let's say we have this crazy looking function. And this is going to model the interaction between two atoms. We saw the simulation last time. The 12th power term, if you care, relates to this, and the 6th power term relates to that. That's great. But sigma and epsilon are positive constants. And then let's get straight to part A. Based on that equation, I claim you could tell me the units for sigma and the units for epsilon. That's a lowercase sigma and a lowercase epsilon there. Any ideas how to approach this? When you first look at this, it seems like, what? And while you're thinking about that, I might as well get the equation written up here so I have it to work with. So that'll be the puzzle for you guys while I'm getting written. How the heck do we figure out units for this thing? All right. Anybody have any ideas? Which one should we start with? you think we should try to figure out what epsilon is or what sigma is?
Sigma.
Okay, how would you approach it? What any guess how you might try to get the units of sigma? I agree. Sigma is the place to start. Let me give you a hint. Let's just forget everything outside the parentheses. Focus on what's inside the parentheses. I claim you can tell the units of what's inside the parentheses just by looking at it.
It must be the same as X.
No.
Is it kind of like in radian form or something like that?
Say again, Alonzo.
Like, is it theta over r?
Not quite. No. Well, let me ask you this. This is a tricky one, isn't it? So it's not obvious. That's why I'm asking you to do this one. So let me get me up there. Whoops, let me get this. We have this crazy looking equation, and I hope you agree that we have sigma over x to the 12th minus sigma over x to the 7th on that inside term. Now, I don't know what this thing is, but let's just call it some new parameter. It's k to the 12th minus k to the 7th, where k is now sigma. It looks something like this. My claim is, what are the units on k? You should be able to tell me right away what the units on k are. And if not, maybe you could tell me one thing they can't be. What if you put in meters? This would be meters to the 12th minus meters to the 7th. Does that make sense? Can I do meters to the 12th minus, oh wait, is this 6th? I think this is 6, isn't it?
Yeah.
Sorry. Gee, I wonder what exponent appears in the answer to part B. All right, sorry about that, but it doesn't make a difference in the question, right? We have something to the 12th minus something to the 6th. Can you have meters to the 12th minus meters to the 6th?
Yeah.
No.
No.
Apples to apples, oranges to oranges, right? Like let's say I had 3 meters cubed minus 2 meters. This doesn't make sense. This is a volume minus a length. We can't subtract them. That's the hint. What has to be the units of everything inside here?
0 or nothing, no unit.
No units, which is like radians, which is what you were saying. And I don't know if that's where you were going with that, but yeah. So what has to be the units of sigma?
No units.
No units. So wait, no. The units of sigma over x has to be no units. So what are the units of sigma? Right?
Units of x.
Yes. Sigma over x has no units. Otherwise, this won't work. That's what I'm saying. So if this has no units, that means the units of sigma have to equal the units of x, which are meters. That's where I wanted you to go with that. What do you think? Is that making some sense? This is a hard one. I probably wouldn't give you one this hard on a test, but it's worth it to kind of stretch your brain and think. You could learn a lot about problems by thinking about the units. A lot. Okay. All right. So already we could tell sigma is some kind of length in the problem. So what does this mean? Somewhere in that simulation we used, sigma had to do with the separation of the atoms and how strong the forces were left, right. So it's a distance, some kind of a distance. All right. Well, if all of this is no units, what are the units on this term epsilon? What do you think? This has no units. What are the units of this thing? What does this symbol mean?
Potential energy.
Yeah, what are the units of energy?
joules or
So it's
electrons?
joules, yeah, or Newton meters, or you could say EVs or whatever, but generally speaking, we just say joules. All right. So, all right, whatever. That's the units. All right. So, in case you're wondering, this term here is some sort of energy scale relating to the bonding energy or something like that, and this is some length scale corresponding to the bond length, something like that. It's not exact, but whatever. All right, let's. All right. So, part B was saying, determine the force. Remind me, how do you get the force out of this? What's the procedure?
FPD.
What's that?
FPD.
No.
Take the derivative of it, the negative derivative.
Yeah. So let me show you right here on the back of the workbook. If we know force and we're trying to get U, we do an integral. If we know U and we're trying to get force, we do a derivative. And watch out for that minus sign. Okay. Now wait, the 4 and the epsilon can pop out. That's a constant. Like that. Let me scoot this a little closer. So far, so good. You could do this any way you want. There's many correct ways to do the derivative. But what I'm going to do is just keep the stuff out front. And then I try not to do too much in my head. So sigma to the 12th. Wait, this is to the negative, isn't it? And negative. I forgot to write the negatives there. When I flip them to the numerator, they become a negative exponent. There we go. So that's going to be sigma to the 12th. That's a constant. The derivative of this is negative 12x to the negative 13 minus sigma to the 6th times negative 6 x to the minus 7th. Now, like I said, there's many different ways to do it. This is just one. I'm trying to let the paper do the work, because if you try to do too many steps in your head, you get lost and you screw up a minus sign, and then you miss a bunch of points for forgetting a minus sign and you get angry. Okay. So now I need to cancel out some of these minus signs. So I'll go in and cancel this one with this one and this one. And so are there other ways to do it? You bet. I could factor out a 6. I think that's right. Questions on that? Doing a derivative, we remembered the minus sign. We had some negative powers. Then I remembered to flip them back underneath it. I look at the units. I know that this must have units of what?
Nothing.
Nope.
Oh, wait.
This had units of nothing when it was both 12s. So this one must be
1 over meters.
right. Okay. And this is energy. So check the units. This is joules, which is, wait, that's a Newton meter times a 1 over meter. Both of those. I get newtons. That's a unit of force. Whoops, sorry. I got a Newton. This is a Newton meter. That's what a joule is. Divide by a meter, I get units of newtons. All right. So there's the force. Let me ask you this. We have two terms here. Which one is going to dominate for small values of x? When x is a small number, Is it going to be a positive force or a negative force? If X is a small number, it's positive if this one wins. It's negative if this one wins. Which one of these is probably going to dominate?
The first one?
Let's see. If I put in 0.1, this would be 0.1, and then I'd flip it up top. That would be like 10 to the 13. If I put in a 0.1 here, that'd be like 10 to the 7th. 10 to the 13th is bigger than 10 to the 7th. Yes. So the force is positive or repulsive. A positive force, you're pushing away from the atom. A negative force, if you get too far away, it keeps trying to pull me back in. All right. This is looking good. So far, so good. Whoops, I lost my page. Let me see what we were doing. I think that was part B. Yeah, that's part B. Okay. Part C says, how do you get the equilibrium positions? Tell me what you would do.
Something about the stable point or the stable area?
Yeah. What else? I want to get a number. I want to know where the equilibrium. Oh, go ahead, Alonzo.
The slope?
Slope, yes. So what about the slope? If I want equilibrium, what do I do with the slope?
It has to be 0.
Yeah. Well, isn't this the slope?
Yeah.
So if I want to find equilibrium, rather than looking at the slope, I could also just do what with this?
Equal to 0.
Yeah, equal to 0, force equals 0, solve for what? I want the equilibrium positions. What am I solving for?
Oh, sigma over x.
X, yeah. So we're going to solve for X. When we do that, let's shortcut. Whoops. Right here. I end up getting 2 to the 1/6 or 1.12 sigma. Okay. So if you're looking for equilibrium positions, this is the technique. Take the force, set it equal to 0, solve for X. All right. Let's get back in here. Now we're talking about the plot. I think we alluded to this last time. I can't remember. So what I did to make the plots was I just set epsilon to 1 and sigma to 1. So basically the energy is in units of epsilon, whatever epsilon is, and the position is in units of sigma. And so right here, what do we get? Well, here I can look. The slope is 0. That corresponds to 0 force. Okay, so it seems plausible that this could be U and this could be F. Let's check it the other way. Right here, the slope is 0. If I take that same point on the graph and go up here, that does not correspond to a 0. So clearly that is not working out. So the upper plot has to be U of X versus X. Now, in this case, again, these units are basically in units of epsilon. So 1 does not actually mean 1 unit. It means 1 unit of epsilon. And here 3 does not mean 3 meters. It means 3 units of sigma. So sometimes you'll see them say in units of sigma, meaning 1 corresponds to 1 sigma, 2 corresponds to 2 sigma, etc. All right. So there's the graphs. Let's take a look here. Obviously, you could plot this in Excel yourself. Let's go to here, equilibrium position. We did that, this, okay. Let's think about this. Let's look at the slope at the various spots and think about the signs and equilibrium, etc. So first off, let's do the easy one. I see equilibrium here. Is it stable or unstable equilibrium? Or is it neutral?
Unstable?
This is it. Here's how you could tell. If it looks like a marble rolling back and forth in a bowl, it's stable. If I push the marble a little bit to the side, it's going to roll back and forth and it's not going to escape. That's stable. So this would actually be stable equilibrium. Unstable is when it looks like that, because if you push it to the left or to the right, it goes away and it never comes back. Is that good on that, Jacob?
Yeah, my bad.
No, you're good. So any other equilibrium here, in your opinion?
Neutral off to like all the way to the right.
Yeah, this is pretty neutral, right? It's extremely flat and not changing. All right, so you could say there's two equilibrium points here. There's a stable at the center here at this special spot, and then you could argue it's neutral out here. Fine with me. All right. What about here? Let me see here. Right here. Is the force positive or negative right here? Remember, this is the U plot. We're looking at U versus X, and I just asked you about the force. Right here, I have a large negative slope on the U versus X graph. That implies the force is positive or negative or zero?
Positive.
Positive. And should it be large or small?
Large.
Big. In fact, it's so big, it would actually be something like this, right? Way up there, right? Because right here at this spot, it's so large, I can't even fit it on the graph because it would make all the rest of the graph so tiny you couldn't do anything with it. So, okay. What about right here? How about right here? Let me let go. So right here, did the force get bigger or smaller?
Small.
And now it's starting to show up on the graph. And finally, when we get to here, whoops, we're right above it here, right? That's this spot right here. That's the equilibrium position. If you recall, that was 1.12 sigma. Remember that? Notice it's right where it should be. And now take a look. The slope becomes positive here. So the force becomes negative. All right. And then what happens is very quickly, we see right about at this point, that's about as steep as the slope gets, it looks like. And then it starts to flatten off and the force goes to zero. And that makes sense. So we see this makes sense over and over again. Let me ask you this. Let's use the marble analogy. If I put a marble right here, would it tend to roll towards the right end of the track or towards the left end of the track? Well, if you put it right here, it should end up way over here eventually. So that means there's a force to the right. Whereas if I put the marble right here on the track between 1.5 and 2, and I let go of it, it would tend to roll this way. Well, that makes sense. We'd expect right here, you should get a negative force, a force to the left. The marble goes towards the left end of the track. Perfect. All right. Let's say I put the marble right here and I released it from rest. So this is at position about, let's say this is about 1.66. So just to give a number to that, let's say this is 1.66. Maybe it's not exactly that, but maybe it's 1.63. Okay, whatever. If I release it from rest, where is it going to go before it reverses direction? We know it's going to go to the left. At about what value would it switch direction and stop moving to the left?
Negative 0.3-ish.
Nope.
Would it be the same height on the other side?
The same height on the other side. Right about here. So it looks like it would be about 1.03. Does that make sense?
I was looking at the wrong axis, but yeah.
Oh, I see. Oh, I see. I got you. He was saying, I understand now. He's saying, well, this is about 0.3. So, okay, you're right. It would go down and then it would come back up to energy level, negative 0.3, which corresponds to horizontal position, 1.03. So the X value would be 1.63 to 1.03. and the energy level would be negative 0.3 to negative 0.3, right? It's going to roll back and forth. Everybody good with that? It's the marble analogy. I know it seems silly, but that could really help you out. Well, go ahead.
Will it roll back and forth, or will it stay at the unstable kind of point? Or is all the energy is conserved? Is that?
Yeah, so we're assuming energy is conserved here. And I don't know if you remember in the simulation, it just bounced back and forth, right? Now think about it. We're assuming that there's no friction here because these are atoms, and we're not rubbing them against a table or something, right? So so we would assume it would go back and forth between these 2 points.
Okay.
Is that good for your question, Detta?
Yes. Thank you.
Where does the atom spend the most time? Does it spend the most time close to the other atom or far apart from the other atom? Remember, this axis here, sigma, is talking about the spacing between the atoms. So as you get to a big number for sigma, a big number for x is in units of sigma. As you get to a large value of x, that corresponds to many sigma, that corresponds to far apart. A small value for x corresponds to very few amounts of sigma. So if I start the atom right here, it's going to bounce back and forth somewhere between 1 and about 1.6 units of sigma from the other atom. Where will it spend the most time? Take a guess.
To the right or to the 1.6?
Over here, right? Think about it. The forces are small. What is its speed when it gets up here? The speed is close to 0, right? And so if your speed is close to 0 and your force is close to 0, there's going to be very small acceleration. It's going to spend a lot of time in this area. So the atom will actually be, most of the time, it will be about that far apart. And then what will happen is it'll come together and bounce very quickly. Now, this is kind of hard to describe, so let me see if I can just get a FET here. I'll bring the animation up from last time. Hold on. Oops. Is it running? And the idea was exactly what we saw here. We see that sigma is some sort of spacing, right? And epsilon is some sort of energy reference level. Okay. And then when I run this thing in slow motion, and let's actually pull it a little bit farther apart. This is almost exactly what we saw. It spends almost no time close to the atom and spends most of its time far away. You can see all of this stuff from these plots. Gee, I wonder why we learn this stuff. It's because you can communicate a ton of information this way to other people who also know how to read the plots. Now, it does you no good if nobody knows how to read the plots, so that's why we have to practice and get good at it. But it's amazing how much information you can store in a graph and tell other people that know the same basic tricks. Any questions while I have the simulation up? All right. I think that's cool. Oh, there's something in the chat. Let's check it. Well, so let's say I start right here. Now I've got it grabbed. It's stuck to my finger. All right. So what I could do is, let's say I take another atom and I ram it together and I shove it together this way. What I've done is I've actually increased the energy so much that it's going to explode outwards and never come back. So imagine you could actually break apart the atom this way. And we know this can happen, right? We know that you can break down these diatomic molecules if you apply enough energy to them. But it gives you an idea of how much energy you need to apply, at least energy epsilon, to the two atom system, right? So if I apply this much energy right here, just under epsilon, it's not enough to break it apart. Whereas if I apply more than epsilon, that's the energy required to break the bond. Just that much is enough, right? It'll never come back now. So you could see epsilon corresponds to the amount of energy required to break the bonds. And that's why it's called strong versus weak, right? Here it'd be easy to break the atoms apart. Here it'd be very difficult. Is that good on that? Yeah. Yep. So obviously the chemistry implications are huge here, right? Okay, let me, whoops, I want this. I want to get back to the screen share. Any other questions while we're at that? I think we're at a good spot to go to the next page. All right. I will highlight, there's a problem right below there, but I think we've basically covered that already. So let me just make sure. If you look right below here, here's some comments. This is that marble analogy. So if you need help with the marble analogy, you could try going through this problem, and I've already walked it out. And again, we've ignored units here. So we're 1.12 units of sigma. All right. Okay, looks like there's a deep thought there. All right, so there we go. All right. Now let's get to this one. Okay. So this is the next page. And now we're going to put in the units and try and fight through it with the units. So the last one, we just kind of got a feeling for it. Now let's look at 8.26. I think if I go just a little bit smaller, I might be able to get it all on the page here. Nope. Okay, there we go. Let's start with that. Okay, I'm going to write it on my whiteboard just so I have it up here, okay? You could take a second to read the question and get a feeling for it. 8.26, I believe. Yeah. Okay. Now, I know this seems a little bit strange, but maybe I'll tell you why we would care about this first. Look at this wording right below. Imagine if we had an electron that's being shared between two atoms. So now you could imagine this might be the location of one atom. This could be the location of another atom, and the electron could rock back and forth and go between the two atoms. So this is a very simplified model. It's not accurate, but it gives you the main idea of what we might care about this for. Okay, so later on, you could imagine something similar relating to an electron shared between two atoms, let's say. Okay, so, all right. And all right, how many equilibrium points do we have?
2.
No, there are
3.
3. So, Alonzo, you saw 2. Where are the 2 that you saw? At what values of x?
Not stable or at negative 1.5 and 1.5.
Yeah, he saw the 2 stable equilibrium. And where's the third one?
The unstable at
Yeah,
0.
right up there. Okay, got it. Okay, so we see there's 3 equilibrium points. Okay. Now, how do we get the equation for the force? Remind me, what do you have to do?
Negative derivative.
Negative derivative. So the first term, we should end up getting a negative term. The second term, we should get a positive term. And the third term, when you take the derivative, should drop out. So what are we going to get when we take that first derivative there? Let me get this up here. Okay, so I know that the force it's that easily forgotten minus sign. It's minus the derivative. Okay, so then the first term is going to give me negative 3.00 x to the 3. This one is going to give me positive 7.50 x to the 1. And the other, well, I guess I don't need to write that. And the other term's done. So hopefully I got that right. Did I screw up anybody, or is that good? This is what I mean about trying to do everything in your head. It's like, oh my gosh. Obviously, you could do this with Wolfram Alpha as well. And you probably should get used to doing that. But, you know, these are easy enough. Excuse me. Oh. All right. So which one of these two terms should dominate? I like to think this way just to get a feeling for the problem. At small values of x, which one of these two is going to dominate for small x?
7.50x.
This one. Yeah. So in the last one, x's were in the basement. We expected the smaller term to be the one with the higher power. Now with the x's in the numerator, we expect the smaller one to be the one with the smaller power, right? 0.1 cubed would be 0.001 versus this is 0.1. So if you get to a small enough value of x, this term dwarfs that one, and this doesn't matter. So we see at small values of x, it's a repulsive force. Okay, that's cool. That corresponds to the graph. At small values of x, if you go to a small positive value of x, the force is away. If you go to a small negative value of x, the force is away. Then as we get out here, right, we saw that it could oscillate back and forth, and we see that there's some equilibrium. All right, we'll worry about that in just a minute. All right. Let me ask you this. How can we get the equilibrium points? I know it's about negative 1.6. Agreed? How can I get the equilibrium points more exactly? What do you think? What's a general way of finding equilibrium points for this type?
When the force equals 0?
Yeah, set this equal to 0, solve for x, you get a couple of equilibrium points. How many should we find? It's a cubic equation. How many possible solutions are there for a cubic?
3.
And that's the 3 that we found. Let's go look at the solution and see if there's something good in there that we could see. Okay, I'm going to bring this all up. Okay, it's not perfect. The upper plot is the graph itself with the potential versus x, the lower potential energy. The lower one is the force in units of EV per nanometer, which is a goofy unit, but it's equivalent to a joule, as we discussed earlier. All right. So now in this case, I set it equal to 0, and I found out it's actually happening at 1.581 nanometers. So here's the solution. If I set that force equal to 0, one solution is x could equal 0. Well, that made sense. We found that one. That was the unstable. And the other situation is solve this, and you get a quadratic, and you can get the square root in there, and that's got a plus or minus sign. So you get those two roots. All of this is making sense. Or at least, let me rephrase. It may not be making sense, but it's all matching what it's supposed to. Sorry if it doesn't make sense. That's my fault. All right. Whoops. Let's get back into the question. All right. Okay. We talked about the units. You already saw it. It's an EV nanometer. Well, let's make sure we understand this, right? So the units of force equal EV per nanometer, I think it was, right? Well, let's work this out. At 1 EV is 1.602 times 10 to the minus 19th joules, all over 10 to the minus 9th meters. Whoops. Sorry about that. My bad. Sorry, let's do that again. The units of force in this problem, right? It's negative units of slope, or the units of slope, basically, right? The minus sign doesn't matter. Well, the rise was EV, the run was nanometers. So rise over run has units of EV per nanometer. When we work that out, it's got units of joules per meter. But recall that a joule is a Newton times a meter. The meters drop out. And so it's basically the same thing as Newton's with a multiplier of about 10 to the minus 10. Okay, because this 9 is going to cancel that and make this 10 to the negative 10. So about a 10 billionth of a Newton, something like that. Okay, let's get back in there. We sketched a plot. You could do that with Excel, or you could use these numbers to do that. Oh, and actually, I drew a graph for you, so you can kind of draw that right in your workbook, so you don't have to use Excel. That'll be nice. Okay. This is a neat question right here. Consider an electron initially located in the left potential energy well. So let's say we have an electron right here at negative 1.581 nanometers. Okay. Got it. And I'm asking, how fast does it need to be going to get over here? What do you think? Any ideas how we could approach this?
Maybe like find the X value that'll put it there for the potential energy. That'll give us like the force, and then we can maybe do like an FBD or something.
Okay, well, let's talk about force here. If I try to figure out the force, let me ask you, is the force going to be the same at these different spots?
No.
No. So I know that we can't just do an FBD, get the forces, and do kinematics. That's not, you could, but then you'd have to do an infinite number of FBDs or a large number of them to get it approximately right. That's challenging. You could do that way in a computer code. You totally could, but that's not a good idea. So any other ideas? We're doing a problem and we're looking for speed. Looks like I picked the wrong week to quit methamphetamines. That's an old movie quote. I don't know if you guys even know that. Airplane. All right. So what is the technique we should use when we're trying to get speed? What's the first physics tool in our physics toolkit I recommended? When you're looking for speed, what type of problem do you do? Do you remember? Go for it. It's okay to be wrong.
Kinematics.
Okay. That would work sometimes, but not in this case. So what's another one that would get us speed? How about this? What are the tools we have? We know we have kinematics, forces, and there's one other one. Chapter 7 and 8.
Work and potential energy.
Good God. Well done, sir. Okay, so we could, all right. So here's the idea. All right, let me get rid of this for a minute. Here's the idea. We have some graph like this. We know the curve goes like this. It's not perfect. We want to be initially at this location. So we know an initial value for X. Do you agree we know an initial value for U? Seems reasonable.
Yes.
So then we could do U initial plus K initial plus work from other crap equals U final plus K final, right? Okay, we want the electron to end up over here. So what should I pick for X final? Remember, this was 1.6 and it was negative. So what value should I use for x final?
1.6 positive.
That's what you'd think, and that's not it. Where's the electron going to have trouble as it goes from here to there?
In the middle at 0.
Exactly. This is where we set x final. Now, here's the deal. If I want the electron to get from this spot over to there, it has to cross over this hill. What's the minimum speed you need to get over this hill at the top, approximately? How fast do you have to be moving to get over this hill? Really fast or just barely moving?
Really fast.
No. You need to be moving really fast down here so that when you get to the top, you're just barely moving. Did that make sense?
Oh, yeah.
You got to go, whoa, I made it. Okay. Right? That's a physics term. Whoa, oh my gosh, it's been a long day. The idea is at this spot, V final is approximately equal to 0. If you can get up to that spot and be barely moving, you're going to make it over here. That's the issue with this one. All right. Did that make any sense?
Yeah, that makes sense.
All right. Now with these problems, we typically ignore this term. We're going to assume that all the forces have been accounted for. I know U initial. Let's bring the graph back up. All right. What's the initial value of potential energy we have for this problem? We're starting right here. Give me a number.
0 at that point, right?
Nope. Negative 3.5. We're starting at that point on the graph in potential land, right? Our x position, x initial equals negative 1.6. I'm getting lazy, okay? Negative 1.6 nanometers. Is everybody okay with what x is and what u is initially and why? We are told the electron starts at this well. That means we're at that position, which corresponds to this energy. Is that okay? There's no force there, right?
Right.
Okay, because the slope is 0, so there's no force. The initial kinetic energy, do we know that, or is that what we're looking for?
That's what we're looking for.
Okay, so got it. So that's just going to be 1/2 mv initial squared. All right. Where do we run into trouble? At the top, right? So what is x final? X final is 0. That corresponds to what value of u?
1.
1. And that's in units of, wait a minute, I wrote nanometers
EV.
here.
Yeah.
Those are units of EV. We would have caught that when we plugged it in, but this is units of EV as well. And then what's the kinetic energy final?
Approximately 0.
Right.
Speed?
It's we were told minimum. See that word minimum down there? That's what gives us this value of 0. If we were any less than that, we wouldn't even make it to the top. But if we're at the minimum value of the initial speed, then we know that you have approximately no kinetic energy at the top. Obviously, any speed greater than this would also make it over the top, but you'd have significant non-zero speed at the top. Woo! What do you think of that tasty meatball? Everybody, is that making any sense?
Yeah.
All right.
Yeah.
Okay, I'm going to pause and see if there's any questions. I think we did all. Now, remember, what is the point of all this junk, right? in theory, there's a lot of different, especially with charges, point charges like protons and electrons. In Physics 163, we are going to do this again with protons and electrons. It relates to electrical engineering, chemistry, a number of other things. Let's call that good. I'm going to pause for questions. All right. Let's get back into it. Oh, okay. So here's two more problems for you. They use the same graph, and this shows you like this might be one way I would write a test question, and this other one shows you a different way I might write a test question. Notice one of them talks about speed, velocity. One of them talks about forces. So we see the two main types of questions you see with these types of problems is, hey, I gave you a plot of u versus x, figure out the force, or how fast is it going, or what initial speed is required, or blah, 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 blah. So these two problems I'm going to leave for you to do at home. But, and notice this one, I gave you a break on the units. We just use joules and meters. So you've got that. All right. Try to make sure you're constantly thinking about that marble analogy, because we're going to fall back on that later in Physics 163 as well. Okay. So that marble analogy is a big deal. All right. And this is where you have to think through the marble analogy, and this one too. So they're all there. All right. I'm going to go another way. Look at this one. Look at 8.31. And let me make this bigger here. Whoops. All right. Let me get this all on the screen here. Consider this one. It's a little bit different in the sense of it looks like I gave you force and x, right? Let me make that just a hair smaller. Sorry about that. There we go. So now, how is this one different from the one we just did? I give you a plot of f versus x, and I'm asking you ultimately to get a plot of u versus x. How do you go from f to u?
Negative integral.
Negative integral. So basically, you just got to keep these straight. And remember, they are on the back of your exam equation sheet. Just showing you again here. On the back of your book, if you forget this stuff. Right there. Right? You've got them right there in case you forget. So it's, yeah. All right. So slow to get these windows back up sometimes. Just like takes all the steam out of me. All right. If not, twiddle your thumbs. Oh man. All right, whatever. So let's, oh my gosh, come on. I don't even know what that question means here. All right, so we've seen a number of these different questions. Before we take our break here, let's go over a few things. What have we learned in this chapter, right? We've seen that there's a couple of different styles here. There's the problems where we say f sub x is equal to minus the derivative of u of x, right? And negative the slope. Right? We've seen some problems like that, and we've seen some problems where you analyze plots. Right? Analyze the two different types of plots. We've seen problems with blocks moving around. And we've seen them on ramps. Sometimes they have friction. Sometimes they have springs. Sometimes they're in or swinging, like they're swinging on a pendulum or something. Remember that? So, and sometimes there's multi-blocks. And the trick with multi-blocks was use two reference levels. We've talked about we use the work done by gravity or potential energy due to gravity, but not both. right? And we talked about basically there's a lot of geometry in there. Sorry, let me fix that up. Glare. All right, whatever. Okay, and so that's pretty much this whole chapter. We're done. All right. Now, before we take a break, I want to I know we're tired, but I want to keep the second half of the class a little bit shorter. So I'm going to just do rapid fire, go through some of these problems, and we'll just talk about some interesting pieces. This will be a review of the stuff from 2 days ago and last time or whatever it was. I don't remember. It's all blending together now. One endless Zoom session. Okay. Oh, I got to sneeze. I'm going to mute. Sorry about that. Okay. So, and we've got three, thank you. So we've got three physics tools, right? We've got forces, we've got kinematics, and we've got, I'll just call it work/energy. Okay. So these are our three tools. Which of the three tools do you need to use to solve 8.29? Take a second to read it. Because if we can't identify which tool to grab, it's pointless me showing you how to use the tools, right? You got to know by looking at a problem what technique you should use or you're lost. So you don't need to say anything right away. Let's give you a minute. Everybody think about it for a minute. Actually, I'm going to get some more water. I'm all out. Go ahead. Sorry about that. I'm just getting really thirsty there. So in this case, which tools do you think we need to use?
Forces and kinematics?
Forces would work, but is the acceleration constant?
No.
So generally speaking, unless we have maybe again, you could code it. We'll discuss that more in about 20 minutes. But yeah, that's not a good idea to use kinematics. So this is the one that jumps out, and that's why it's a chapter 8 problem, right? Because don't we have an initial height? We've got reference level here. So it's begging for a work energy approach. However, read this. The problem says something about normal force at over the top of the lower hill. So it's talking about normal force right here. That's what says to do an FBD. Right? And then obviously it's accelerating towards the center of the circle. Otherwise it wouldn't be moving in circular motion there. Once you identify those things, right? The fact that we're going to use that equation and U initial plus K initial plus work external non-conservative if it exists in this problem equals E final. I'm running out of room. That's K final plus U final. Once you identify that, the rest of the problem is easy, pretty much, right? It's getting your heights right, writing down your minus signs right, you're good to go. All right. This next one, whoops, or any questions about that? It's just kind of to get a feel for how you would approach it. Okay. How about this next one? We're supposed to try to sketch these different things. To be honest, this problem is probably a little challenging, but it's a good review problem. So this is a really good problem to kind of review and think about. So let's just attack the first one together. I want the potential energy due to gravity versus time for a block on a plane as it slides downwards. So first, tell me, is the potential energy due to gravity going to be a constant, or is it going to be changing? Let's start with that.
Constant.
And what makes you think that the potential energy due to gravity will be a constant?
The ramp is linear. and-
Okay. So let me ask you this. What's the equation for gravitational potential energy? You're right that the graph is linear. But what's the equation for potential energy due to gravity? M. Do you remember?
MGA.
GH.
MGH is the height remaining constant. No.
Why it changes?
So we expect in this case, the height is going down. So what should happen for the gravitational potential energy?
Decrease.
It should decrease. Is it going to decrease linearly or at some non-linear rate? Is it going? So we know it's going to decrease. It starts up here. Let's say this is U and this is T. We know it's going to go downwards, right? So is it going to be a straight line? Is it going to be a curved line like that? Or is it going to be a curved line like this? Which of those curves do you think? Top, middle, or bottom?
I'd say bottom.
Okay. Why do you think that? Kind of what's going on in your brain? It's okay if it doesn't make any sense to me. I don't care. Just try.
Because it's linear.
What's that?
I'm guessing myself now.
Well, let me ask you this. You said this one, the lower plot, right? That changes most rapidly at the beginning. This block is going to accelerate. It's going to be moving most quickly at the end. That means gravitational potential energy should be falling off more like this one, right?
Yeah.
Isn't this a good problem? So you could try to think about this stuff and walk through it, but yeah, whatever. All right. So hopefully I didn't screw up the plots in there, but I actually used equations to make plots. And so it turns out this is the point of this problem. Sometimes if we try to guess and kind of think it through, we will screw it up. By having to make a plot, it forces you to think at a deeper level. And that's the real reason I have so many stupid questions with plots in it, all right? Because every once in a while, you can clear up a misconception when you're making the plot because you're like, wait a minute, this doesn't make sense. I feel weird. All right, so plots are useful. That's it. All right, let's go to here. This is kind of a fun one. It's a standard block on a ramp with a spring and there's some friction. I think you could figure that one out. Here's another block on a ramp. All right, cool. You can see that springs, there's a number of spring problems here. All right, let's get to this page and we're almost to the break. Hang in there. I swear we're almost there, people. So this is a classic physics problem. Think about this. We're going to use, this actually uses all three physics tools, right? We use energy to figure out how fast it's going as a function of angle. We could use an FBD to figure out when the normal force goes to zero so that it loses contact. After that point, we do 2D kinematics to figure out where it lands, right? There you go. That's why it says excellent problem. It's got it all. How about this one here? Ball on a string. We've alluded to this in previous problems. You can actually figure out the speed at the top or the bottom based on an energy problem, right? You could say, well, if I know the speed at the top, well, like this, it says, okay, this is the tension that's going to break the string. At that point, that's going to happen at the bottom of the swing where I know tension is up, mg is down, and I know MAC is up. Oh, well, let me just write AC, okay? So in this case, I could do an FBD to figure out this. If I want the speed at the top, I could do an energy problem because I know the change in height. And then I could do another FBD. Isn't that crazy? Yeah, and then this was kind of fun. Is it possible where it could be on the verge of breaking at the bottom while at the verge of falling out of the loop at the top? Is it possible? You could try and figure that out. All right, we're almost there. Just showing you the tools that we use. You can start to do a huge number of things with just these first 8 chapters. Bungee cord jumping. If you want to understand bungee jumping, here you go. This is all there. This is just a cool, weird thing to watch. There's an old Veritasium video you can watch where if you drop a mass by itself and wish the chain, which one hits the ground first? Is it a tie? Oh, yeah. And this one, page 29. This one, what I did is I wrote up a bunch of things that students sometimes think are true, which are not true. And so I was imagining you have a block that's sliding down a circular ramp. And I say, how come we can't do this? And then I explain why you can't do that. And then another student says, well, wait, I think it's this. And I explain, hey, this still doesn't work. And then, oh, sure seems like we should learn how to code. If we're going to do that, we need to understand momentum. Oh, shoot. That's the next chapter. Why don't we call this good for this live stream? Take a 10-minute break.